Hello, my name is Gustavo Aguilar and I'm going to present my evidence too. First, we have to know what is a discrete time state space model. It defines the relation between the input and the output in state space form, where is the value of the discrete state at the previous sample time instant. The input is a vector of length, the output is a vector of the length, and is the number of states. Then we have the state feedback with an observer. In control theory, state observer or state estimator is a system that provides an estimate of the internal state of a given real system from measurements of the input and output of the real system. It is typically computer implemented and it provides the basis of many practical applications. In the third part of this evidence, we have the model of the last assignment. We use that. In my case, I use the second model, which is a third order level. In this part of the code, we convert the given transfer function into a state space model. Then we have to check the controllability and if the model could be observed. Here, CTR equals to CTRV phi gamma. CTR is a matrix which gives us the value of 0 or 1. And if it's 1, that means that the system is controllable. And the other matrix OVS is to know if it could be observed and if it has the same order level of the model, that means that it equals to 1, so it could be observed. Then we convert the plane into a continuous plane, so our plane is going to be an S plane. Here we can change the poles. Uh, the objective of this evidence is to design a state feed controller, uh, and state feedback controller with an observer. So that's why we have to make sure if we could add like a observer. Then we have the observer. Using the function place, we get the gain of the observer. With this, we can obtain the last matrix, which is the one that explains the AC generator with the controller. This matrix is in the state space model. So we use as I said, the function place to know the matrix. And in the last part, phi c equals to phi minus gamma times LV. KV times C phi minus gamma times LV minus KV times C. That is our matrix of the observer. Here in the fourth part with poles, it is easier to change the poles on the S plane because the damping ratio and the frequency are easier to change the values. So here we have the original poles in the observable equals 1, and then we transform our poles into a continuous time state space model. So we get our poles in S. So I think that's it. Also, the dumping ratio I use 72, I think. Yeah, 72.68. And in frequency, my frequency was 7.08. So I use those values and that's it. Finally, we have to make sure if our system applies to these three things, 3 points that are poles inside the unitary circle. That means that it is stable. So we have here 4 poles, and all of them are inside unitary circles, so that means that our system is stable. Then on the bot diagram, the resonance peak when is equal to 3 dBs on the x-axis, we have to make sure that when it's 3 dBs, it is greater than 5 rads per second. And finally, we we saw that our total time of our system or our function was 1.72. So it is less than 2 seconds. That means that our system is correct. Finally, for my conclusion, I'm really happy because I think that I actually learned a lot of control these 10 weeks. It was really tough, but studying and watching some videos of control, I could successfully understand, I think, the part of theory. Um, Also, I learned some MATLAB and how to use Simulink because I didn't know how to use it, and that is really interesting. Interesting. And, and the classes were interactive, but I think the last part was really difficult. How to know when to use discrete time or continuous time and change between these two states. It was like really confusing, but I'm happy with my I'm really happy with this subject. The subject really liked me.